Imagine that you have this situation. You have a light source which sends light out in all directions, and at some point or the other, you have a receiver. Now, in the absence of any media or anything, the light ray that the receiver receives will come from the source in a straight line, since that's the shortest path between the emitter and the receiver. But in the presence of physical media, this is no longer going to be true. If there's no physical media, or you're in a media of a constant nature, and I ask the receiver what direction you should travel in to get to the emitter, he'll just point you along the straight line that he sees the light coming in along. Imagine that the emitter is in one media, a vacuum maybe, or air, or glass, or water, and the receiver is within some other medium. It's possible that the path that the light ray takes from the emitter to the receiver will still be just a straight line, but there's a principle called the principle of least time. So we're going to have to think about the speed that the light has in the first media versus the second. Also, the distance. I'll call the perpendicular distance from the emitter to the interface A. The perpendicular distance from the interface to the receiver will be B, and the horizontal distance from the emitter to the receiver will be called capital D. A and this B and D are all constants. A given light ray emitted by the source will strike the interface at some point or the other and then continue traveling till it reaches the receiver. If there wasn't a change of medium, then certainly this would be a straight line. In other cases, it might not be so. I'll call the horizontal distance from the emitter to the interface point X. I'll call the horizontal distance from the interface point to the receiver Y. Obviously, X plus Y has to equal D. I'm going to call the angle that the light path in the first media makes with the right angle direction to the interface theta 1, and I'll call the other corresponding angle theta 2. This angle must be 90 degrees minus theta 1. So since the angles have to add up to be 180 degrees, this angle must actually be theta 1. Likewise, this angle is theta 2. That angle must be 90 degrees minus theta 2, and that angle must be theta 2. So I have two right triangles. We know lots about right triangles. If I know the lengths of the two shorter sides, I can easily calculate the hypotenuse in either case. This is important because the hypotenuse of each triangle is the path along which the light ray travels in the given medium. The distance traveled in the first medium is radical a squared plus x squared, while in the second media, you have radical b squared plus y squared. Since I know the speeds in the two different media, I can now write down how much time the light ray I can write down how much time the light ray is in each medium. The first one will be the distance in the first medium divided by the speed in the first medium. Then I'll have to travel from the interface point to the receiver. The distance is radical b squared plus y squared. Divide that by the speed in order to get the time. The total time is the amount of time spent in the first medium plus that in the second medium. A, B, V1, and V2 are constants, so this is a function of x and y. I'd like to make this as small as possible in order to have the path of least time. If I didn't know any better, I would say make x equals 0 and y equals 0. That'll certainly make that function as small as it can be, but that's no good. X plus y is supposed to add up to some positive number d. Making both of them 0 won't do that. I have to instead impose a side condition. X plus y must be d. So I want to minimize a function of two variables subject to a side condition. This is the setup that we had for the method of Lagrange multipliers. I've drawn my triangles in because I'll need them when I reach my conclusion. The gradient of f is straightforward to calculate. F is the sum of two things, each one of which depends on only one variable. The gradient of g is easy to calculate. It's a constant vector whose components are both 1. The differential condition says the gradient of f must equal lambda times the gradient of g, and generally speaking, I have to include my side condition as well. In this particular case, though, life is easy. X over v1 radical a squared plus x squared equals lambda, and so does y over v2 radical b squared plus y squared. That means that x over v1 radical a squared plus x squared must equal y over v2 radical b squared plus y squared. On the other hand, sine of theta 1 is opposite over hypotenuse, x divided by radical a squared plus x squared. And likewise, for sine of theta 2, I might satirically call this Snail's law. Actually, it's Snell's law. This relates the angles of incidence of a light ray at an interface between two media to the speeds. This principle of least time will morph into something called the principle of least action, which will eventually lead you to something called the Euler-Lagrange equations, which are of fundamental importance in modern physics. I hope that everybody has a good day. I'll talk to you again soon.